the reason that I post the lecture, so I see there's like 2 people online. Well, so last week, well, not last week, just Monday, that we covered the basics of high frequency response, how it look like. We started by looking at a high pass filter and a low pass filter, and then look at how the body plot look like. And then we went to show MOSFETs, look at the high frequency equivalent circuit, where the capacitance was forming between the different connectors. It creates a huge impact on the output later on, as we'll see. And we did draw the circuit, and we also simplified the circuit by eliminating the capacitors that have minimal impact. And then we left only the capacitor that has a large impact on the circuit. And then we were able to derive the gain, the unit or the current gain of the circuit. So when we look at the current gain, basically we apply an input current at the input side, and we short output so that we can get output current, short circuit current. By shorting out the current, we short basically this one. We also short this one. The circuit becomes very simple. So through that, we can write the expression for input current and output current, and eventually we're able to solve for the current gain. When this current gain goes to 0, because if you look at this current gain, it's a function of the capacitance and GM, but these are pretty much constant. So it is a function for S. S is equal to J omega, which means when omega change, this whole thing is going to change. When this whole expression becomes 1, which means the gain is 1, the unit gain is where we can find out what this S is. And we define that S or omega to be GM over this. You can derive from the expression. So we call this a kind of a threshold frequency. This dominates what happens with the high frequency response. And we'll see this again later. So this is for the MOSFET. So if you go to the BJT, the phenomenon is very similar. In fact, if you look at the GPT, if you look at the symbol for GPT of a BJT, it's going to look like this. I can take an N-type BJT, and this is the base, collector, the emitter. Each connection has a metal. So between each metal, there is capacitance. So therefore, you can imagine that this will be 3 capacitance, one between gate and collector, another between a base, not gate, between base and the emitter, and another one between collector and emitter. So typically, the one between collector and emitter, just like the MOSFET between drain and source, is very small. So typically, we can get this one basically neglected. So now you're left with 2 capacitors only. So if we draw the small signal circuit of the BJT, you can figure out that the BJT, the small signal has a pi model. With the pi model, we have R pi, and then we have GM times V pi at the output, and then we have this RO for the circuit, and this is your emitter, this is your collector, this is your base. So you can see this is the BJT model without the parasitic capacitance. So now we have capacitance between base and the collector and base and emitter. Now we can neglect again the collector emitter, so we can add the capacitor. So between base and collector, you add it here. And between base and emitter, you add it here. So this circuit now becomes this one, and you have another one you can connect here. So we call this one C pi, and we call this one C mu. And this is your input side, and the output side and on the C side. So if you look at this circuit, this is pretty much similar to the previous circuit we had for the MOSFET, except this one R pi over here. For MOS, there's no R pi. That's the only difference. Otherwise, the capacitor are going to be added. They call different names. The book also gives you equations, how to calculate like C pi, C mu, CGD, CGS, and so on. I really don't care, how, because those equations are physical equations from physics. People have derived it. As long as you know where to get it, that's okay. You don't have to remember those equations. But the most important thing for us is to understand what are the impacts of this capacitance. So for this BJT, you know that the only difference is R pi. So potentially, and we're going to have, we can draw the equivalent circuit to get the short circuit again. So similar to the MOSFET, when we have the short circuit again, we short the output to get the current, short circuit current, and then we apply an input current at the base. Then we take the difference, we take the ratio between output current and the input current, and we'll get the gain. So apparently now the gain is going to be a function of some of the capacitance going to be in part of the expression. So in order to do this, as you can see, at the output side, this is shorted. Shorted means this is shorted, so this is gone. And also, because this is shorted, so basically this is also ground, because this is shorted, right? So this is ground, so this is all ground. So if this is ground, like 0 volts, and what is voltage over here? And we can assume it's V pi. As you can see, this is V pi, this is V pi, and this is ground. So right away, you can easily write the current. So what is the current over here? You can see that the current, let's call it IC, because this is current at the collector. The current IC will be this current over here minus this current. And that current down is GM times V pi. Minus the current from on the C mu. So the current on C mu is the voltage across C mu multiplied by S C mu. So 1 over S C mu is the impedance, right? So now you have, so because the voltage on both sides, one side is V pi, one side is 0. So therefore the voltage is V pi. So basically we can have this one as C times S times C mu times V pi. So you got this IC calculated. And on the other hand, we can also write IB, which is the current, let's call it IB, which you can see the current is this current, plus this current, plus this current. There's 3 currents out of that node, out of this little node, right? So we can write IB as V pi over R pi, that's one current, plus another current is SC pi times V pi, and plus another current is SC mu times V pi. So right away, you can get the ratio, which is the current gain is IC over IP. The V pi is going to cancel, so we get GM minus SC mu divided by 1 over R pi plus SC pi plus SC mu. So this is the expression you have. Well, in this case, if you get the actual numbers, you'll find that GM is much larger than SC mu. So GM is a quite large number, and SC mu is very small, even for the high frequency operation. So therefore, you can neglect this one. So if you neglect this one, we get a approximate expression is going to be GM. And also, we can multiply R pi on both denominator and numerator. So this becomes 1, and we take S out on over here. So it becomes R pi times S times this 2. And then the above is GM times R pi. So we got a very simple expression. This becomes 1 plus S R pi C pi plus C mu. And can you guys tell me, what is this number? What is GM times R pi? Do you still remember? What does that give you? In a BJT, huh? What is it? Beta. Yeah, so this one is actually your beta. So beta in the middle range. I mean, when you don't consider the capacitance, so we call it the middle range gain. So that's your beta, and in the future, we're going to call it beta 0. And this bottom becomes same thing, R pi plus C pi plus C mu, okay? So this, as you can see from here, so this is your gain. As you can see, if your S is very small, if your S is small means this term is small, so your gain is actually your middle range gain. So when S is small, so low frequency. So the middle range now becomes available. But if S is big, this whole thing started to decrease because this number is going to increase and the whole thing decrease. So, or normally beta is 100, right? So or normally beta is about 100 for BJT. So this number started to be like a very small, 0.0 something. Yeah, go ahead. Yeah, ICOIB is better. Yeah. Yeah. No. So when S start to increase, this whole number is going to start to decrease from 100 to 99 to 98 to 50 to 10. Eventually, you'll get to 1. That point getting to 1 is what we call the unit gain, right? When the output is the same as the input current. So that's called unit gain. So at what time would this become a unit gain? Well, this becomes 1. Well, you basically, in this case, you have to take the absolute value because this is complex. But for simplicity, let's say, it's going to be 1. So we take this one to be 1, and then you have this beta. So we take this one beta 0 over 1 plus S R pi C pi plus C mu equal to 1. And then you, as you can already imagine, when this whole thing equal to 1, which means this term becomes really small. So basically, you could take the absolute value to include 1 in it, but I mean, you basically can neglect it. So neglect that, this becomes like this. So this becomes gone. And then you move everything on this side, and also we replace beta pi back into GM times R pi. So now you can see what happens. The R pi cancel, and you got S, you replace S with omega. So you got omega equal to GM over R pi, no, not R pi, C pi plus C mu. And we call this omega t. We call this omega t. So we got this frequency. For the BJT. And if you want to plot this one, you can plot this one and you will get really same thing like we get from before. Is this look like this? Okay. And then this is where the here is a 3 dB, what we call a 3 dB. I didn't plot a good, yeah, probably here. So a 3 dB is where you got this frequency, you can plot it over there. So that's what you have for basically what happens when you consider the capacitance of each of these BJTs and MOSFETs. So far we have been able to calculate FT or omega t for both, which is based on the short circuit gain. But in fact, when we look at amplifiers, most of the time we're not looking at the short circuit gain. Most of the time we're really looking at is the voltage gain. So we really have to get back to look at the amplifiers and look at voltage gain, how the capacitance will impact the voltage gain. So this is a better plot than what I did last week or last lecture, is to illustrate how the frequency plot will look like. So for low frequency, basically around here, we call it the base frequency, where you have the omega t. Below there, your amplification becomes almost a constant. And of course, it's closer and closer to a constant when it becomes less and less. But over at this point, really, the gain drops to 3 dB. If you take 20 log that gain, you get drop 3 dB. And this 3 dB, we call this bridge frequency. And then the output will attenuate, or the gain will attenuate 20 dB every decade for this particular application. And in the future, we'll tell you that sometimes the actual gain will drop more than 20 dB per decade, like 40 dB, 60 dB, and so on. By 80 dB, it's no longer stable. So the most that you can get is 60 dB decrease per decade. And 60 dB is a lot of attenuation, because 60 dB is 1,000. 10 times 1 times 20 dB, 140 dB, 1,000 attenuation is 60 dB. So that's a 60 dB attenuation per decade is very much. So, but in this plot, it's 20 dB per decade attenuation. So we talked about this last time. So the goal today, hopefully we can finish the talking today, is we're going to look at this section 10.2, and we're going to look at the section 10.2 is look at common source and common emitter amplifiers, and we observe what is the actual impact of this capacitance on the voltage gain. So in order to get voltage gain, apparently we need to start with the equivalent circuit. In this case, we have a common source amplifier. And in the common source amplifier, you notice that we basically draw the small signal circuit only. We didn't draw the current source. We didn't draw the voltage source, the DC part. So everything was close to a small signal. On the input side, the gate, we have an input voltage, and we also have a resistance. That resistance represents the internal resistance of your input voltage source, which always exists. But for clarity, we will find later on today is that without that little resistance, the performance of the circuit is totally different. It's very interesting. So with that resistance, you have one performance, but without that resistance, your performance is totally changed. So having that resistance there represents more a real world application scenario. Okay, so for this one, we have a small signal circuit over here, but we didn't replace really with a small signal circuit. So now we can actually draw the small signal circuit. And you all know how to draw small signal circuit now, but remember, at this time, we need to include the capacitance. So the initial small signal circuit was this one, plus the open circuit at the input side. So when you have an open circuit, that RS IG doesn't make any difference because it's an open circuit. There's no current, right? There's no voltage drop, so it doesn't make any difference. But now with capacitance connected, the whole circuit starts to make a difference. So this is a small signal circuit. I'm not going to redraw it. You should practice, like without looking at the book, how to draw the small signal equivalent circuit. This is very important. So by the time we have the small signal equivalent circuit, we can do the analysis. Basically, our goal is to find a VO. Our goal is to find a VO. And then once we find a VO, we find a relation. And this is your voltage gain. So that's our goal. Now you might already notice that, well, for this circuit, we have like 2 nodes, 3 loops, because these two can be combined. These 2 resistance can be combined. RO and RL can be combined. So basically, you can combine this one. We can remove one of them. We use this one like RL prime. Then RL prime is equal to RO in parallel with RL. So that one you can simplify, right? So we already simplified one component. So now you have really, if we remove the whole thing over here, you look at how many nodes you have on this circuit. I mean, it's basically 3 loops and 2 nodes. You can easily write a nodal equation on the 2 nodes. And after you write the nodal equation, you can easily solve for the output and the input. But even though this only has 2 nodes, but because the capacitance exists on the capacitance, the equations will be a little bit complicated. And because the expression is a little complicated, it does not sometimes give you the exact insight. Like, what are you looking for? The unique characteristics. What does it tell me? It's not very clear from those equations. So even though you can do it, but it's not that easy to find. What does it mean? Like, sometimes you get a really complex math equation, but you don't know what it means. You can get a number. Yeah, you can get a number. You can get an expression, but it does not tell you the exact what it's doing. So for that reason, we're going to do some simplification. Okay, so the simplification says, well, the first step again is to combine RO and RL to make it simpler. And then because it does not make much difference, I mean, it's exactly the same. And then by looking at the circuit, we're going to now start the simplification. So in this class, actually, a lot of times you'll hear or make a simplification. So if you ask, at what time can you actually make this kind of assumption? What I can tell you is that if the difference is 100, you can make an assumption, fairly accurate. So if the two numbers, if the one number is 1, other is 100, you can make a 1. Or if one is 0.1, the other is 10, or whatever, if one is 10, another is 1,000, you can safely make an assumption that you will still get very accurate result. The output will be different by 1%. Okay, so that's where you can really make an assumption. So the assumption we're going to make here today is that because the current the CGD is fairly a small capacitor, so the current between G and D, so which is this. If we write the current between G and D, what we can say is, suppose the voltage here is VGD. As you can see that VGD equal to VG minus VD. And VD in your case is VO. So it's VG minus VO. So you have VGD. And then the current IGD equal to VGD times VGD times C times S times C GD. So and then the current on this branch, here, at the capacitor of CGS. So let's call it IGS equal to S times CGS times VG. If you get the actual number, you plug that in, you'll find one interesting phenomenon, is that IGD is much smaller than IGS. Okay, so that's one observation basically. Now, of course, I don't have the number to show you, but you have to trust me. A lot of people have done that. And for that reason, we can assume, so for that reason, because IGD, maybe let me do this way, maybe more accurate. Maybe no, maybe this is not accurate. What I should have done is GD is much less than GM times VGS. So this is also VGS. Yeah, this is VGS. So this is VGS, VGS. This S is 0. So S is here. So IGD is much less than GM times VGS. And GM times VGS is the current in this branch, which means if this current is much larger than IGD, the current through RL prime is going to be all, in other words, I can get VO equal to GM times VGS minus minus IGD times RL prime. This is also minus sign here. Because VGD is so small, because this one is so small, so which is equal to VGS times RL prime. So this is what we get. So VO can still be approximated to be GM VGS times RL prime because IGD is very small. Now, of course, you might say, okay, I don't know how small it is. Could I include it in the future? I mean, definitely you can do that. But you will be disappointed to see that, well, that number is actually so small. Why should I have done such a complex work to include it, right? So that's basically the argument. So once you have VO given, you can see that I can plug VO over back to get VGD. So once I get VGD, and then I can plug VGD to get IGD, which is a small number. Now you might say, okay, you already neglected. Why do you calculate it again? Well, the idea is that that number is small, so that's why I made a mistake earlier. Even though that number is small, but IGD and IGS, these two are probably comparable, which means even though we can neglect IGD when we calculate output, we calculate VO, we can neglect. But when we calculate at the input side, the IGD and VGS, they're no longer have a big parity. So we need to consider it. So that's why do here. So now we have this one derived. We have VGD and we got IGD, and then we have IGS. We can IGS. We already wrote the equation here. Now we can write another equation is VSIG equal to RSIG times IGD plus IGS, two current. So one current going this way, one current going this way, and then minus plus VGS. And then VGS, we already calculated VGS, which is VGS equal to, in this case, is S times CGS times IGD. So you got all these numbers, and you can plug this in. So eventually, what you get is really, in the book, they will tell you to find this because earlier we calculated IGD. So now what they're saying, okay, if that IGD is calculated, if IGD is already calculated, now I'm going to use a equivalent capacitor here, CEQ. So if IGD is calculated, so this will be equal to, the new equation will be VGS divided by impedance, which is S times C EQ. So then we will say, okay, so CEQ equal to IGD over VGS times S. So this is the same thing. We got this. So from the previous circuit over here, from this circuit to the other circuit, the difference between CGD and CEQ, you can see CGD is measured between G and D. The voltage between G and D, we went through a series method to calculate it. But when we plot that CGD into ground, apparently the voltage is changed. So that's why you have this voltage on CGD, on CEQ is not on CGD, that's different. So based on this, what we're doing is we simply calculate IGD. So we maintain IGD the same. If you maintain IGD the same, which means the current over here is going to be the same. And the voltage drop here is going to be the same. The voltage here is going to be the same. So that's the idea. So that's really, and this step, to be honest with you, has no physical meaning. It basically is a mathematical transformation. It's just saying, okay, I want to maintain input side voltage in NAC. I want to maintain the input current the same. I don't maintain the voltage at the gate is the same. Therefore, I have this circuit basically to represent that circuit. It's the same thing mathematically. But this mathematical transformation makes a huge difference because now you see what happens between CGS and CEQ? They're in parallel. When two capacitors in parallel, what do? You can they become one capacitor, and the value is when two capacitors in parallel, the value add them. Okay, you add the value. So basically, if one is 1 micro, the other one is 1 micro, you add it to it's 2 micro. Okay, so you add them, it becomes 1. So once it becomes 1, and the circuit will look like this. And this is VGS. So now you can find, okay, if this is VGS over here, this 2 becomes a voltage divider. This 2 becomes a voltage divider. So from VSIG, we can easily get the voltage of VGS, and we use GM times VGS, and then times RL prime, we get the output. So all we need to do is really erase some of the stuff so that we can get space to do what we want to do, is we can write this VGS equal to VSIG over RSIG plus S times C. This is CGS plus CEQ. This is VSIG, okay? So we got VGS. And then we have VO equal to minus GM times VGS times RL prime. And VGS, now we plug in this in. So you can figure out the math. It's very simple. It becomes minus GM times VSIG times RL prime and so on. So then we can get the gain. So the gain is going to be VO over VSIG and equal to minus GM times RL prime divided by RSIG plus S times CGS plus CEQ. So this is the equation we have for the voltage gain. Okay. So we have the voltage gain. As you can see now, your voltage gain has an omega at the denominator. So which means if S is small, what happens? Oh, I made a mistake. Actually, I was missing the voltage divider. I have to, these two impedance. No, actually, sorry, this is totally mistake. I have to redo it. Apologize for that. Let me redraw this. And I need to make this right. So the circuit becomes impedance is 1 over C times S times C. So basically, VGS is going to be VSIG divided by RSIG plus 1 over S times C GS plus CEQ, and then times this S over C CGS plus CEQ. Sorry for the previous mistake, because this is a voltage divider. So voltage divider means the actual capacitor is the voltage we need, and divided by the total impedance, and then times VSIG. And then we have VO equal to GM and minus GM times VGS times RL prime. So now we can calculate a voltage gain is going to be VO over VSIG equal to, so that VSIG cancel. So we have minus GM times RL times 1 over SC GS plus CEQ and divided by RSIG plus 1 over. Now we can, in this case, we can multiply S times CGS plus CEQ on numerator and the denominator. Then we get minus GM prime, then 1 plus RSIG times CGS plus CEQ times S. So this is what we get for the voltage gain. Okay, so now it's better. So we have the voltage gain at this. So now what we can see is that if S is very small, which means this term is very small, the voltage gain becomes minus GM times RL prime. This is what we get, supposed to get for the open, for the middle range, middle band gain, which means this is 0, S is very small, or more than 10 times smaller. But when S start to increase, this whole thing start to increase, and that's why over here, you see here is the middle range when S is very small. So when S gets to the point, to FH, is the cutoff frequency from here to here, we have 3 dB. And you will see that this S is something. Okay, and we will derive that. And when S continue to increase, to like 10 times more than 1 or 100 times more than 1, and then this 1 becomes nothing. If this 1 becomes nothing, you can see your gain is inversely proportional to omega by, again, 20 dB. So if you take the 20 log AV, you will get that. So now let me see if I have, now I need to derive this, okay? So if you look at this, what it really means is that we're taking 20 log AV. We're taking 20 log AV. So if you take 20 log AV, it is equal to 20 times log, and this number becomes GM times RL divided by 1 plus this omega squared RSIG squared times C squared. That C is the total of CEQ plus CGS. So you can see, I think I want to ask you guys, if I plot this curve as a function of frequency in a logarithm, at what point, at what frequency do I get to this point, the green line in the middle here? What this number would be? Exactly, that's 1. Because when this is 1, this is 1, 1 plus 1 is 2. And 20 log 2, basically 20 log square, that 2, that gives you minus 3. So 20 times this, it gives you minus 3. So this becomes 1 is what we need to look at. So which means if we look at that is 1, we get omega equal to 1 over R SIG times C GS plus C EQ. So this is what we get for the frequency, and we call this omega H. Okay? This is what we get. And the actual green line, or the blue line, whatever, green or blue, this blue line is the actual 20 log AV, the actual plot. The dotted line is approximate. So I guess this guy called Bode, he developed this method. Okay, forget about that little curvature at the corner. Let's extend the horizontal line to that point, and then extend the slope also to that point. You got a cross point. So this is very useful. So in the future, you might see plots. Well, they don't plot this actual line anymore. They plot the blue line as a line, as a straight lines to this point and the straight line to here. But in the mind, people know that this point here is not actual gain. It's actually approximation at that point, but the actual gain is 3 dB over here, or minus 3 dB in this case. So that's what we get. So the actual, this gain is, the middle range gain is your GM times RL, because if this is very small, your gain is log GM times RL prime, okay? This should be a prime, and don't forget the prime. Right. Right. So your gain, when this omega is very small, this term is gone. Your gain is GM times RL 20 log. So this line over here, the horizontal line is 20 log GM RL prime. Well, GM and RL prime, they both positive numbers, so you don't have to really put that vertical lines there. But this line over here is really the omega start to drop. Omega start to increase and again start to drop. So this is where we really get interesting to look at the gain. So in the previous example, we have RSIG as the internal resistance of the input source. In rare cases, I say rare cases because it doesn't happen very often. In rare cases, that input voltage does not have a resistance. Or in some cases, it's so small, you can think it's not there. So when RSG is so small that you can neglect it, the whole thing becomes a little different. But in the book, I don't know why, but they did add a CL at the output. You represent some sort of output capacitance, but don't pay attention to that. So that doesn't really matter anything. So we can do the same thing, combine RO and RL and so on. But the input, see, ISG has no resistance. You see, right away, I think you can already notice why is that SIG makes a huge difference. Because if you don't have that, you see what happens with SIG? It's in parallel with the capacitor, VGS, CGS. It's in parallel means that CGS doesn't do anything. And if that CGS doesn't do anything, what is VGS? VGS is VSIG. So basically, over here, what you're saying for the circuit, okay, I can basically neglect it. Or I can neglect this one also, of course. And then the whole circuit becomes, and then this is your, this circuit here is VGS GM times VGS, right? Yeah. Because again, that CL may be so small that in comparison to RL, it does not add any difference for the gain that you calculate. But by next week, we'll tell you that if you have some sort of capacitance, and then it will impact the low frequency response. So generally, it does not impact the high frequency response, so you can neglect the low frequency response. But if I do this, I have a problem because there is a capacitor CGD over there. So which means if I calculate GM times VGS, like what I did last time, use VGS, GM times VGS times the RL prime, I get the output voltage, but I actually neglected IGD. And we said what before was IGD is small, which basically in this case, if we neglect CGD or IGD, the whole thing does not have any impact. The capacitor does not have any impact on the output. So in the book, what they said, okay, now since the input is are still small, we can neglect with CGS. Let's not neglect CGD. See what happens. It might have some impact now because previously what we did was what we said is very small. So and then by doing this, you can see here. Let me erase this things, and we can do some. Do some calculations here. Let me equation here. So IGD. So because this VGS equal to VISG here, see here, the voltage here, same as voltage here. And this is VO. So I can calculate IGD equal to VGS minus VO times SCGD. And VGS is equal to VSIG minus VO SCGD. Okay. And then we have VO equal to minus GM times RL prime, then times VGS. Okay. So in fact, this expression is not accurate. Let me redo it. Do it in a more accurate way. So VO equal to minus GM times VGS. And then actually this is the plus sign. Minus IGD. So I got this current over here, minus the current over here, got the current over here. Now I have minus sign outside. I have times minus 1, then times RL prime. So this is what I get. Now, however, IGD in this case is super small. So therefore, we can write VO equal to minus GM VGS RL prime. So now we have, if you wrote this one and you get this one, now you have your gain becomes VO over VSIG equal to minus GM RL prime divide, or nothing else. So this is what your gain is. So it does not impact the output if you neglect the GM times VGS. So in fact, if you neglect the VGD. So if we don't neglect VGD, then we'll be able to plug in IGD over here, and then we can get VO. So let's write it. So VO equal to minus GM VGS minus IGD is VGS minus VO times SCGD. and then yeah, times RL prime. So you can see the difference here now is one VO in here. So we're going to plug in this one to get the actual GM VGS times RL prime minus GS SCGD. Actually, RL probably can be outside, and then minus and then plus VO C S GD times R prime and so on. So now you basically have this term on this side. So you have to move this term to this side in order to get VO. So you can write VO. So I'm not going to spend the time to write this anymore because this really is a little bit just mathematical manipulations. So once you write VO, you can plot the equations. And then in this process, I did not include CL, but in the book, it does include CL. So when it does include CL, the final expression I want to tell you is that I can write down so that we can all together. So the final expression is like this. When you include, well, in this case, if you want to include CL, you can know that the CL really the total impedance at the output is going to be RO prime RO in parallel with RL and in parallel with 1 over SCL. That's output. So this is equal to RL prime. So you basically replace this RL prime with this one, you will have the equation with SCL cascaded. So the final expression given is A equal to VO over V SIG. I'm going to write this equation so you guys, we can discuss what it means. GM times RL prime. In this case, actually, this 1 minus S times C G E over GM. 1 plus S times CL plus CGD times RL prime. Now I want to take it back is that in this case, they did say that RL prime is this, not including CL. But what I mean is that if you go back to the slide, what I had was, if you replace this RL prime with that, you can get all the numbers here. So, but in this case, RL is RO over RL prime. So if you look at this equation, you probably understand a little bit why they have a CL over here. Because eventually, the output has something to do with CGD. If there's no CL, then the expression is a little bit different. So, but this expression, what it tells you that you have 1, 0, and 1 pole. So if you have a 0 and a pole, you know what it means? Is that if S is very small, let's say S is so small that the whole expression here is much less than 1, what happens? Is very small. What do you AV? If S is very small, the numerator becomes 1, the denominator also becomes 1. So your AV is minus GM times RL prime. So if S is very small. Okay, what happens if S is very big? If S is very big, which means that one is much larger than 1, and this one is also much larger than 1. And then that S will apparently will cancel, and you move this CGD over C. I mean, we have to take the absolute value, but the minus sign is going to cancel. So you get this RL, and then you get GM on the top, and you can move the GM on the bottom, and then you have CGD up there. So we got all gain. Oh, the GM is going to cancel, RL is going to cancel. So RL cancel, GM cancel, and you have really the output is going to be, so AV is going to be just CGD over CL plus CGD. Okay, so that's very big. So you probably notice that in this case, if S is very small, you got a constant. If S is very big, you also got a constant. So that's why we have this plot over is constant and it's constant. And these two frequencies here, this is your pole, and this is your zero. And the zero and the pole, they have a certain distance, and we can calculate these two values equivalently. We get this. So this is your pole here, and that's your zero. Okay, so your pole basically is SQ2. At the bottom is really RL is 1 over RL times C L plus CGD. And your zero equal to 1 over CGD, 1 over CGD, yeah, CGD over GM. So we can move GM up there. So you get 1 pole and 1 0. So that's why this plot looks a little different like this. Okay. So in the middle, your output is going to be attenuated 20 dB every decade between these two frequencies, between your pole and 0. Then we can calculate the gain at 0 and the pole and again 0, and it's well-cropped point. Okay, so what is this point? This unit gain. So we can also calculate what is unit gain, what's the frequency, you get a unit gain as well. So this is fairly simple after you derive all the different equations. So that's what I think. What really this says is fairly simple. If you simply know how to draw the small signal equivalent circuit, you know where to put the capacitance, and you know how to solve this like a complex circuit. Either you know how to solve it, or if you know how to simplify them. But those conditions to simplify them, it's just I have to remember them, because I mean, once you get actual exercise, when you do your homework, you'll find actual numbers. But if you want it, you can plug in those numbers and see if that is going to make a difference for you. So we can do that. So after we finish the common source amplifier, then naturally we would go to common emitter. Now with the common emitter, we already know that the circuit is pretty much the same, except this R pi. So if we draw the equivalent circuit, and you know that the difference between these two is simply add R pi. When the R pi is added, the current IB on the input side is slightly different than what we had in for the MOSFET. The MOSFET does not have R pi. But since it's R pi and C pi are in parallel, so in theory, it does not make it too much more complicated, but just some really simple derivations will do that. So since we already done MOSFET, what we did was we tried to get the middle, the CGD, to simplify it. You can use the same idea to simplify C-mu here. So you can think about, okay, well, I can use, because that between B and C, the current is very small. So basically you can neglect that current by calculating the output, and then the process is exactly the same. I'm not going to repeat it here because it's the same. But the end result is that I can, now this is combined. This is combine RL and RO, and over here we have C pi over here, and we also we also combine these two. This is one question some students ask me: how can you combine RSIG and R pi? Well, see, we can do a source transformation. So basically for this part, we can transfer it into our current source and ISG in parallel. So by doing this, you can have this one is VSIG over RSIG. So now you see here, if I do this R pi becomes parallel. So what I do is I can combine these two into one resistor, which is called R pi prime. Or what they call here? They call it ISIG prime. Okay, so this is the current. And by doing this, you can further change them back into a voltage source. And this becomes ISIG prime. And this, however, this voltage is no longer VSIG because this voltage is actually prime is that current with VSIG divided by RSIG. Now you multiply by R pi plus SIG. So this is this, okay? And then this is in parallel. This is so RSIG is in parallel prime. RSIG is in parallel with R pi. So after doing this, if you look at this circuit, this is exactly identical with the MOSFET circuit, exactly identical, except that VSIG is prime and RSIG is prime. That's all. So basically, you change a little bit. The gain ratio changes a little bit. So we're not going to repeat it here because it's the same. We're going to do in the same procedure. You can find the gain, and then you can find the gain. So maybe for reference purpose, I can write down the values. Probably that won't make much difference either. So you guys can review the book and draw. So the important thing that you have your middle band gain, and you have this 3 dB gain, and then you have this minus 20 dB drop for BJT as well. So by this time, you can already basically conclude, well, this MOSFET and BJT, they have similar performance at high frequency. The middle band, of course, they also have similar performance as well, but the equations are slightly different. What I want you to complete the lecture is with one more little thing. This is very simple. It's called Miller's theory. So often in the future, actually, even in the previous circuit, you already know that over here, previously it was a capacitor like this, and with something like this, and with something on this side. That's the previous circuit. But what we did, we transformed them into this, and this. In fact, there is a capacitor over here, but this capacitor here is so small, we neglect it. But how do you do that? Is what we did was by doing some mathematics, we look at IGD small and things like that. But in fact, there is a theory you can easily do that. And this will be very useful. We're probably going to use this quite a few times in the future. That if you have an input voltage, output voltage, and you have some sort of impedance in the middle, and if you know the ratio between V1 and V2, like the ratio, if you know the ratio between these two, you can simply convert this circuit into this circuit. This is called a Miller's theorem. So for Miller's theorem, because you need to maintain the input output exactly the same, so therefore the equations has to be written in a way that in this case you have V1, I, and you have I and V2, and you have these numbers, they're not multiplied. I mean, the input current, the input voltage, the output voltage, output current. So on this side, you have different I1 and I2. It has to be the same. It didn't change. But V1 should not change either. But in this case, in the earlier case, you have V1 coming in minus Z times I, that gives you V2 gives you K times V1. So that's the equation for this guy. But for the second circuit over here, well, we have V1 equal to I times Z1. And then we have V2 equal to I times Z2. So, and then V2 equal to K times V1. So we got this equation here. So right away, you can see what is Z1? Z1 is V1 times divided by I. And Z2 equal to K times V1 divided by I, or equal to V2 divided by I. So we got these two numbers here. Because the we have also we also have in this here we have also have this equation is V1 equal to so we have V1 minus Z times I, and it equals K times V1. So we can solve for V1 here. So V1 equal to so V1 here. So V1 equal to Z Z times I divided by 1 minus K. So we have here from this equation we got this. So now we plug in this V1 to here, or V1 to here. We can get a Z1 equal to V1 is so I cancel. So V1 equal to Z divided by 1 minus K. And Z2, so Z2 equal to K times 1 minus K times Z. So we got this. So this is very useful expression in the future. So if you know V1, V2, you know the relation between V1 and V2, this visual K, and you know Z, you basically can separate that equation by this. Now, if you have input voltage or current or whatever you have, or output whatever you have, this makes very simple. So by this time, if we go back to the previous circuit we have, we can basically break the middle capacitor into these two capacitors, one on this side, one on this side. But one on the input side makes a big difference, but one on the output side is very small, so we can neglect it. So that's what really we have for the resistance. So, this time is so good, so we finish it. So we're gonna skip section 10.3 to 10.5. Okay, so, but if you guys have time, you can read it because this basically is from different perspectives to look at how to calculate the gains and frequency impact. I also posted homework because we're skipping some sections, so homework is a relatively small set of homeworks, and they both still done the same day. So this way, I didn't have to change the homework numbers because the previous, otherwise I would combine this 2 in 1 and I have to change all the homework numbers. But just give you guys a chance, if you meet the one homework, at least this one will give you a whole credit for that homework, for each smaller homework. So we are gonna have a quiz next week. Already, I didn't post the contents, but I think I already